All right, my friends, let's see how it went. So for the process of elimination, that's where you do a combination of multiplying equations by scalars, so scaling them up or down, of course, evenly on either side of the equation to keep the equation balanced, and then either adding or subtracting rows. You'll notice that I have a tendency to never, or at least try to never, subtract equations. I'll always try to turn it into a situation where I can add equations. The idea is adding is way easier to do than subtracting. Anyway, so with that said, for part A here, I hope it makes sense that really you could just take row 1 as it is and add it to row 2. And then what would you get when you did that? So if you add 3x and 5x, you get 8x. Take 2y and negative 2y, add to 0y, which is why this was such a great problem to start on, and 4 plus 8 equals 12. And so here you can see, just by adding the two equations together, you got the y terms to eliminate out. And how come? It's because I kind of set you up to have that perfect opposite situation. And that's going to be our goal in problems that are a little more challenging, is to set ourselves up to have perfect opposites. So when we add the equations together, that term will be eliminated. Okay, so now I'm just going to divide both sides by 8 and then reduce my fractions. So 12 over 8 reduces to 3/2. Okay, and then from here, you could do elimination again if you want, but most people don't. We usually switch gears and kind of switch to back substitution. So you could take 3/2 and you could back substitute it into either equation, whichever one looks easier to you. I kind of like row 1, so I'm going to take 3/2 and I'm going to substitute in for x right there in row 1. And so then I would have 3 times 3/2 plus 2 times y equals 4. Okay, and then just at this point, you just solve for y. So let's see, what would that be? 9/2 plus 2y equals 4. Subtract the 9/2 over, and 9/2 is 4.5, so you get negative 1/2. And then divide both sides by 2, aka multiplying both sides by 1/2. So I'm going to show it like that. And then you'd have y would be negative 1/4. There we go. Okay, just like in the previous lesson, when you write your answer, since basically you were finding when two line graphs intersect, we're just going to go ahead and write our solution as an ordered pair. So your x coordinate is 3/2 or 1.5, and your y coordinate is negative 1/4, where those two lines intersect. There you go. Okay, now let's look at part B. Some people at first look at part B and kind of feel a little frazzled, I think, because of all the decimals. But you can scale equations up or down as needed, okay? So what I'm going to do is just clear the decimals out like this. So I'm just going to do 100 times row 1. And so if I did that, then I'd end up with, instead of 0.02x, I'd have 2x, and then minus 5y, and then equals negative 19. And then I'm going to do the same thing to row 2. 100 times row 2 would give me 3x plus 4y equals 52. Okay, now before I move on, I want to talk with you about notation. I want you to notice that I am not, I repeat, not putting parentheses around the entire equation and popping a 100 on there, indicating that I'm going to multiply the whole thing by 100. That's considered a no-no in math writing, because operations should never span across equal signs like that. Okay, so if you have a habit, I'm just going to go ahead and label it as a bad habit, of writing your scalar multiples in that fashion, I'm going to encourage you to switch to the notation that you see here, where I'm basically saying what I'm multiplying the entire row by. It'll keep you out of trouble when math gets bigger and harder later. Okay. All right. So with that said, now let's look at trying to get, so this is equivalent to the system of equations that I had up above. I hope that makes sense. And then really I just want either the x's or y's to eliminate out. So we could eliminate the x's or the y's. It really doesn't matter. It's just a matter of like what seems easiest. What seems easiest for you with your arithmetic and doing things without a calculator and all that stuff. Okay. So I'm going to go ahead and try to get the x's to eliminate out because I just like the idea of smaller numbers. So I'm going to multiply this new row 1 here by negative 3. Okay, so instead of 2x, I'd have negative 6x. Instead of negative 5y, I'd have positive 15y. And then instead of negative 19, I would have positive, let's see, 3 19s. That'd be 3 less than 3 20s. So that'd be 57. There we go. And then I'm going to multiply row 2 by just positive 2. So I'd have 6x plus 8y equals 104. Okay, now I'm going to go ahead and add these together. So why did I do it that way? I really was trying to set myself up to have opposites with the x terms to get them to cancel out. So you also could have done y terms if that was easier for you. So I'm going to add these together, and I'd have 23y equals, what is that? 161, I think. Yes. There we go. Now I'm just going to divide both sides by 23. And 161 divided by 23 is 7. Let's check that. 23 times 7 would be 140 plus 21, which is 161. There we go. Okay. All right. Now that I have the y value, now I can just back substitute and get the x value. And you can back substitute anywhere in your work. You can go back up to one of the original equations. I prefer not to because of all the decimals. Or you could go anywhere in your work. And so what I'm going to do is take y equals 7. And where do I want to put that in? I think I kind of like row 2 for this. There we go. So I'm just going to replace that y with a 7. And then what would I have? I'd have 3x plus 4 times 7 equals 52. 4 times 7 is 28. Let's see, what's 52 take away 28? There we go. Okay, divide both sides by 3 and you get 8. There we go. All right, don't forget you were finding where two lines intersect, and so they would intersect at the point 8, 7. Don't forget to put the x coordinate first and the y coordinate second. There we go. So far we've had 2 single solution problems, right? Linear equations are commonly single solution problems, right? Because you've got one line, and as long as it's not parallel to the other line, you should have a single solution. So there you go. So let's look at part C here. Part C, let's see, I don't know, let's eliminate x's. So I'm just going to multiply row 1 by 2. Oops, 1/2 times 2 is not 2. 1/2 times 2 is 1. Okay, and then I'm just going to take row 2 the way it is. And then let's add them together. And what would I have? Well, I'd have 0 x's and 0 y's. And then on the right side, I'd have 13. And so, so here we have this universally false statement. And then you may have done this differently, in which case you might not have 0 equals 13. You know, you might have, I don't know, you might have something else, some other universally false statement. But here's what math is telling you. Sure, you know, those two lines will intersect as soon as 0 equals 13. So my friends, this is math telling us no. This is math telling us that these two lines, if you were to graph them, that they would have been parallel. And so they won't intersect. There's no combination of x and y terms that could make both equations true at the same time. And so your conclusion, my friends, is going to be that this is a no solution problem. So therefore, there is no solution. And if somebody asks you to explain, you could just explain that if you graphed the two line equations, they would have been parallel. Now, I do want to make sure, though, that nobody thinks that the answer here is parallel lines. The answer, they asked you to find a solution, and the answer is that there isn't one. And so the answer is what I have in the box here. The reason, or graphical reason, is that the two lines were parallel. So hopefully that makes sense. Okay, part D, let's look at this one. Part D is very similar to part C. I almost copied it. But there was this one subtle difference. So when you go about your work on part D, maybe you do 2 times row 1. You'd get 6x plus 16y equals 1. And then when you add row 2, you get This time you don't get a universally false statement. You get a universally true statement. And this time math is telling you that it doesn't really, that pretty much any combination of X or Y that satisfies one equation would satisfy the other one as well. And so when you get this universally true statement, that is an indicator that you have infinitely many solutions. All right, now this used to be the end of the problem in Algebra 1 when I teach this, and sometimes in Algebra 2 when I teach this. We just say infinitely many solutions and we move on. But it's time for us to be specific about what we mean. So in this class, we're going to expect you to define the infinitely many solutions. Because when we say infinitely many solutions, are we saying that anything on the entire xy plane, would work? No, we're not. There are infinitely many solutions, but they would have to be in just the right spots of the xy plane to work. So let's talk about where they'd have to be. Well, in order for something to be a solution, it would have to at least lie on the line graph that you were given here. So like, I'm just going to go ahead and solve for y for this first line. So 8y, I'm just going to subtract the 3x. Whoops. And then I'm going to divide both sides by 8. There we go. So this is the equation of the line graph that you were given. And I want you to notice that if you were to do the same thing with row 2, just isolating y, and then divide both sides by -16, notice you get the exact same equation. And that's why we got this universally true statement, and that's why we're saying that there are infinitely many solutions. But where would the solutions have to be? Where are these infinitely many solutions? Well, they are the points that lie on this line. So I'll just like sketch a little picture, just pretend that this picture is amazing. Anyway, the point is that when you graph the first line and the second line, they are the same line. So the points of intersection are any point as long as it lies on this line. So when we say infinitely many solutions, we're not saying just anything on the xy plane. We're saying the infinitely many points that make up this line. So at this point, you're going to be expected to define those infinitely many solutions. And this is how we'll do it. We'll say infinitely many solutions of the form, and then we're going to write it as an ordered pair, but you'll have formulas instead of constants. So I'm going to write this in terms of x. So your x could be anything, but then your y value would have to be calculated using this formula. So you take your x value, you multiply it by -3/8, and then you add 1/16. And you would use this formula for every single x value that's from the real number system in order to calculate all the solutions that are on this line. There we go. All right, my friends, hopefully that makes sense. Another way to answer this problem correctly, I'll just say AKA, would be to say infinitely many solutions of the form. Practice the way that I'm writing this when you do your problem set. Even if the back of the book doesn't write it like this, practice this little sentence so you're ready for test questions like this. So of the form, and then I had written my answer in terms of x. Every once in a while, you might find it handier to write it in terms of y. I wouldn't say this problem is one of them, but let's say with one of the equations, I decided to solve for, instead of solve for y, I solve for x. So maybe I subtract that 8y over, and then divide both sides by 3. So another way to express the exact same thing would be to say infinitely many solutions of the form, and then to have your answer in terms of y. So y could be the free variable, but your x value would have to be calculated using this formula. So you take your y value and you multiply it by -8/3, and then you add 1/6. So this time your y value is free to be whatever it wants, but your x value would have to follow this formula in order to be calculating points that are actually on that line graph that you're given there. And then don't forget to say for all x from the real number system. Now notice we're saying for all x from the real number system. We're not saying like in the past we've said for all x from the integers, you know. And the difference is that if you were to just use all x's from the integers, you wouldn't get the infinitely many points that are on the line. You'd just get like evenly spaced polka dots. But if you want the entire line graph, then you'd have to use all the real numbers. So hopefully that makes sense. Okay, so these are the nuts and bolts of solving a system of equations using elimination. So make sure you're okay with single solution problems like parts A and B. Make sure you'd be okay with a no solution problem, like how to know when you're getting a no solution problem and what that meant graphically. And then for part D, make sure you're also okay with not just finding out when you have an infinitely many solutions problem, but also being able to define the solutions in kind of this ordered pair form where we're using formulas in there, okay? So look for practice in your problem sets for stuff like that. Okay, now moving on to example 3, just giving you a little more practice with some story problems. So here we've got a plane takes about 6 hours to fly 2,400 miles from New York City to Seattle, Washington against a headwind. At the same time, your friend flies from Seattle to New York City. His plane travels the same average airspeed, but his flight takes 5 hours. Find the airspeed of the planes and find the average wind speed. So just some vocabulary. Airspeed, what they mean by airspeed here is if there was no wind, how fast would the plane be moving? And then wind speed, of course, is how much the wind is affecting the speed of the airplane. So hopefully that makes sense. Check in with me in the next video and we'll see how you did.